All right, geometers, welcome to another super nerdy day of home learning. All right, today we're talking about sections 11.5, 11.6, which are different proportions with area and volumes. We're going to talk about just some polygons and their area, or solids and their volume or surface area, and how that relates to similarity. All right, so what we have here, you guys, is we have three similar solids. All right, and we're going to just kind of talk today about the relationship between their similarity ratios, okay, and their ratios of their areas and volumes. All right, so first thing you'll notice, like if I look at these two figures, they're both cubes, and the similarity ratio from one cube to the other, remember similarity ratio is simply the ratio of corresponding sides, is simply 1 to 2. Or from figure 1 to 3, it'd be 1 to 3. Or from figure 2 to 3, it'd be 2 to 3. So when we ask for similarity ratio, we're just asking for any linear measurements that correspond, and we make a ratio with those. All right. So we can go ahead and put that in our little table here. What is the similarity ratio from figure 1 to figure 2? Well, it's simply 1 to 2. Any pair of corresponding side lengths or edges that I match up, I'm going to get a 1 to 2 ratio. What's the similarity ratio from figures 1 to 3? Well, it's just simply 1. That has this edge is a length of 1. And this edge is a length of 3. So it would be 1 to 3. And then finally, what's the similarity ratio from figure 2 to figure 3? And same thing, if I just look at their little corresponding edges here, this has a length of 2. This has a length of 3. So it would be 2 to 3. So now we'll look at the ratio of areas and the ratio of volumes. So to do that, we first need to find what their surface area and volumes are. All right, so let's talk about surface areas first. So surface area is all the little square units that are on the surface of this cube. All right, this is a three-dimensional cube, and if you ever play dice, you know that a die is like a cube and it has 6 sides. So each one of these faces is a 1 by 1 square, so 1 square unit. All right, but there are 6 of them. So the surface area of this cube is 6 square units. All right. Now on this figure, each surface, remember there are 6 faces to this cube, but each surface is 4 square units. All right. I know that looks like a 3, but I was just trying to highlight it in there. All right. So each surface is 4 square units times 6 faces is 24 square units. All right. And then in figure 3 here, I see that each face has a total of 9 square units. All right, kind of shade in one of the faces, and there are 6 of those faces, and 9 times 6 is 54 square units. All right, so there are all of our surface areas of these solids. Next, the volume. Volume is how many cubic units, so how many 1 by 1 cubes make up each one of these. This first figure is just 1 cubic unit. The second figure, you'll notice there are 4 cubes on the front layer and then 4 cubes on the back layer, which gives me 8 cubic units. And in figure 3, you notice there are 9 cubes on the front, and then a second little layer of 9 cubes, and then a third layer of 9 cubes. So it gives me 27 cubic units. So I'm going to use these values now to find the ratio of their areas. All right, so from figure 1 to figure 2, the ratio of the area would be 6 to 24. Looking at area, 6 to 24, but that simplifies to 1 to 4. All right, and from figure 1 to 3, this is 6 to 54. All right, and 6 to 54 simplifies if you divide them both by 6 to 1. Oops, wrong place. 1 to 9, and then finally, from figure 2 to figure 3, this is 24 to 54. And if you divide them both by 6, you end up with 4 to 9. All right, so the ratio of areas was 24 to 54 divided by 6 gives you 4 to 9. And then finally, ratio of volumes. All right, so from figure 1 to figure 2, the ratio of volumes is 1 to 8. Cannot simplify that. We leave it as 1 to 8. From figure 1 to 3, the ratio is 1 to 27. It gives me, can't simplify, 1 to 27. And then finally, from figure 2 to figure 3, the ratio of the volumes is 8 to 27. Again, that cannot be simplified, so we're going to leave it like so. And here's what we notice. All right, we're just going to make comparisons between how the similarity ratio affects the ratio of areas and ratio of volumes. All right, so see if you can recognize a pattern here. All right, this similarity ratio is 1 to 2. Notice if you square 1, you get 1. You square 2, you get 4. Notice if you cube 1, you get 1. And if you cube 2, you get 8. What you should notice is that if you take each of these similarity ratios and you square them, you get the ratio of areas. So if this is a 2 to 3 similarity ratio, 2 squared is 4, 3 squared is 9. And what you'll also notice is if you take each one of these similarity ratios and you cube those numbers, because now we're dealing with cubic units with volume, you get the ratio of volume. So here's what I know. If the similarity ratio is some numbers a to b, the ratio of the areas will be a squared to b squared. And the ratio of the volumes will be a cubed to b cubed. All right, so this is the relationship between similarity ratio and what the ratio of the areas and volumes would be. And in these problems, I'm going to refer a lot to the table. When I refer to the table, I'm talking about these different values. All right. Now, one other thing I want to point out is when you're doing these problems, similarity ratio will always be the same for any linear measurement. All right. Anything you can use a tape measure for, linear measurement. So like for instance, perimeter would have the same as the similarity ratio, or circumference be the same as the similarity ratio. Ratio of areas would be anything that has to do with area. Maybe you want to talk about how many gallons of paint, for instance. Well, you use a certain number of gallons of paint depending on the size of the area that you're painting. So maybe paint or wallpaper or something like those problems that we did in the area chapter. And then for volume, right? Obviously, we talk about volumes of liquid or something. But also, I will give you problems that deals with weight. And when we're dealing with weight, you're going to have objects that have the exact same density. So anytime you're dealing with a problem with weight, because they're going to have the same density, their weight is simply determined by their volume. So you're going to use this ratio for weight. All right, so let's just take a look at an example of how we can apply this. All right. Well, I guess before we do that, let's talk about the rules. All right. So when you're solving these problems that have similar polygons and you want to, or similar solids too, and you want to apply this stuff, the very first thing is determine what ratio is given. So maybe you're given the side lengths and you could determine the similarity ratio. Or maybe you're given perimeter, you can determine the similarity ratio. Maybe I give you the area of two polygons. Well, then you would know the ratio of their areas by setting up a fraction. Maybe I give you the volumes of two polygons or the weights of two polygons, or rather solids, I should say. Sorry about that. Then you would use the ratio of volumes. So as we do examples, I'll point out where I'm going to plug into my table. All right. So then we're going to take that ratio, put it in our table. Then we're going to solve for other ratios in the table. And then we'll use the needed ratio, whatever the problem asks for, to set up a proportion and solve. So I know this seems a little abstract for now, but once we do a couple examples, it'll make more sense. All right, and these are the steps I'm going to follow. So here we go. If two similar polygons, so you have to know they're similar, have areas of 128 and 50 square inches, what is the similarity ratio? So step one in my process is determine what ratio is given. Well, what ratio is given to me here is the ratio of areas. I'm given the areas. I know that one area is 128 square inches, and I know that the other area is 50 square inches. Right? That is step one. What ratio do you have? I have ratio of areas. All right. Step two, simplify the given ratio before you put it into the table. Well, this fraction simplifies. These numbers are both divisible by 2. And when I divide by 2, I get 64 square inches to 25 square inches. This is the simplified ratio of areas. The next step is to plug into the table. All right. So here we go. Or this is part of that step. Simplify and plug it into the table. So here's my table. We've got similarity ratio That's for anything linear. We got ratio of areas. And we have ratio of volume. Okay, so I'm going to put whatever ratio I have in the appropriate spot. Now what's given to me is the ratio of areas. So that's going to go right here into my table. Now as a reminder, here's the relationship of these. If this is a to b, this is a squared to b squared, and this is a cubed to b cubed. So here's what I know. I know the ratio of area is 64 to 25. Well, if I know the ratio of areas, to get the similarity ratio, I simply just need to square root those numbers. And this is why simplifying it was really helpful. And I promise you, the problems I give you, when you simplify it, you'll get perfect squares or perfect cubes to make the problem easier. So if I would have just plugged 128 and 50 into here, I most certainly would have not, I would have had a harder time doing it, because when I went to square root that, they're not perfect squares. But when I square root these, if the ratio of areas is 64 to 25, then the similarity ratio is 8 to 5. I simply square rooted them. Now, I know this problem doesn't ask this, but it's worth pointing out. Once you know the similarity ratio, to get the ratio of volumes, you simply cube the numbers. So if I wanted to know that, 8 to the third power is 512, and 5 to the third power is 125. So the ratio of volumes would be 512 to 125. Now, let's see what the problem actually asked me for. So I determined what ratio was given. I simplified it, put it in my table. I solved for the other ratios in the tables. Now, if you're asked to solve a problem, which I'm not in this case, then we would do step 4. But I don't need to do step 4 because the problem simply asked me, what is the similarity ratio? Well, look, it's right here. The similarity ratio for those two similar polygons is 8 to 5. And we're done with that problem. All right, I'm going to stop here, and I'm going to make a second video with the other examples, because I'm going to run out of time on my ability to screencast here. All right, so just go to the second part of this lesson, and you'll see the remaining examples worked out.